Okay, so first I would like to welcome everyone to the short course on Bayesian nonparametric data analysis, which will be taught by Peter Mueller. The course is jointly organized by the Biostats program from McGill University and the Centre de Recherche Mathématique à Montréal. Peter, it's a great pleasure for me to introduce Peter Mueller, who completed his PhD at Purdue University. As he says in his summary a long time ago. Then he joined the stats department at Duke University and moved to the Department of Biostatistics at the MD Anderson Cancer Center, and recently joined the new stats program at the University of Texas at Austin, but remaining adjunct faculty at MD Anderson. He was the president of the International Society of Bayesian Analysis in 2010. He's a fellow of the American Statistical Association and the International Society for Bayesian Analysis. He is well known for his works on Bayesian inference, Bayesian nonparametrics, and he is also interested on simulation-based methods and optimal design and multiple comparison procedures. And he's one of the authors of the book on Bayesian nonparametric data analysis. And I'm really pleased, as I said, to introduce Peter. Peter, thank you once again for accepting this invitation. It's a great honor to have you with us.
Thank you. Thank you for the chance to present here. And welcome to everyone. So here's the plan. As you can see here on the title slide, that's already a quick executive summary of what we want to do. See here on the left side, you see like, here's the data. So the data are these pins here. It's essentially the empirical distribution of, it's an empirical distribution. And in the nature of the experiment is that we don't see the frequency at 0. Because the frequency of 0 means there's no reads, there's nothing recorded, so we don't get to see it. And we want to make inference on what could be there. Actually, I can quickly tell you what's the application. This is counting the number of distinct T cells. So the total number of distinct T cells is a measure of the strength of the immune system. So you really want to know how many are maybe out there, but we're just never sampled. So you want to know the full distribution. If we try to fit a parametric model to the observed data, if we were to fit a parametric model to these guys, then it would completely determine the missing one at 0. But it's of course missing something, like it's not necessarily, I don't know, Poisson or whatever, or geometric or whatever you might want to fit. There could be some uncertainty about it, and to properly quantify that uncertainty and understand it, we need a probability model for the unknown distribution. Down here is the unknown distribution, let's call it F. We need a probability model for that unknown distribution. And inference and probability models for unknown distributions, that is generally known as nonparametric Bayesian inference. Or a bit more general, nonparametric Bayes is about Bayesian inference for infinite dimensional quantities, in this case the distribution, and it could be other things. Here on the right side, the right panel is again the same story. There's some unknown distribution here, say something like this could be the underlying distribution. And we just get to see like some points and want to make inference about the distribution. In this case, it's actually a random effects distribution. And in this particular case, we're actually very interested in the inference. We'll talk more about that example later. We're interested about the probability of that left upper corner under this underlying unknown distribution. So again, it becomes important that we can fit the distribution. So we need a probability model for this unknown F. We need a P of F. And again, that is an issue of a nonparametric Bayesian prior probability model. So I want to talk you through such models. That's where we are headed. In a bit more detail, quick plan of what we're up to. First 30 minutes or so, I plan a quick review of Bayesian inference and posterior simulation, mainly just to establish terminology and notation a little bit, and so you can get used to my accent and everything. Then for the rest of this course, I plan to do today on Monday, we'll do density estimation. Density estimation is simply the statistical inference problem that corresponds to probability models on an unknown distribution. Then tomorrow on Tuesday, we'll talk about regression, where I like to think about regression. I like to think about regression as inference on a family of distributions, let's call them G sub x, that are indexed by covariates. In a way, that's what regression is about, right? For a given covariate, you want to have a distribution of the outcome of interest. And on Wednesday, we'll talk about clustering, like random partitions, and a bit more generally, probability models for random subsets, all of which turns out to be closely related to random distributions. And I'll still talk you through all the details. If we have time, we'll still talk about hierarchical priors at the end on Wednesday. That's the plan. That also means you can see there's a list of items, there's a list of inference problems and models I would like to talk about, but nothing happens if you don't make it all the way down the list. So don't hesitate to ask. If you have just some quick clarification question, please feel free to just unmute and speak up. Like if something is unclear, just unmute, speak up. For bigger questions, maybe either use the chat room or you can, I think there's like a button where you can raise your hand for a question. And every once in a while, I'll stop and I'll ask for questions, and then we can see if there are any questions out there. So let's start with just a high-speed review of Bayesian inference. If you have never heard of Bayesian inference at all, this would be way too fast. If you already know Bayesian inference, it's probably terribly boring. For those of you somewhere in between who kind of know it, and just it's good to have a refresher of terminology and notation. I hope it's useful. So let's consider the following kind of sampling model. The story to this sampling model, the story to this distribution could be we want to learn about the dose response curve and their patients. So I equal 1 to n might be patients, might be indexing patients. And each patient is administered a dose. So patient I gets dose di, and there's an unknown probability of success at dose di. Success might be tumor response, or the headache goes away, or whatever it be. Pi sub di is the unknown probability of success at dose di. Sorry, I misspoke. This is very bad. In the way how I wrote it here, I would not index patients, it would index doses. Then D sub I is the ith dose, and then N sub I would be the number of patients who are administered that particular dose DI, and then YI is the number of patients out of those NI who show a response. So forget all that, my sampling model is simply binomial sampling. I have binomial sampling where the success probability is indexed with a parameter theta, and we want to learn about the parameter theta. If we have n observations, like there's n doses, and for each dose we observe a certain number of patients, then the joint likelihood, the joint sampling model for all of them. So this y is now a vector of y1 through yn. The joint likelihood for all of them would just be, assuming independence, it would be the product of these binomial sampling models. And I was being a bit sloppy here. If we are only interested in the theta, like theta is the parameter of interest, as far as the theta is concerned, I can ignore the binomial normalization constant, and I just write what appears there on the right side. Like I copied the binomial kernel that involves the theta, the unknown parameter, and I already ignored the normalization constant. So that's the sampling model, and that would be the same that you would use in classical inference and frequentist statistics. The one-line summary of what Bayesian statistics is about appears now in the next line. In Bayesian statistics, what we do is we augment that sampling model, we augment it to a joint model on the pair of y and theta, simply by multiplying with a marginal distribution on the unknown parameter. So just by augmenting the sampling model, we make it a joint model on parameters and data. So at this moment, the data here, just to point that out, the data would typically also include things like missing data or future data. And the parameters might also include like additional hyperparameters. But one of the nice things about Bayesian inference is we don't have to stress out on what we call parameter and what we call data. Like sometimes it's not obvious. Missing data, should you call it a parameter or should you call it data? It actually doesn't matter, because when all the smoke clears, what we have is we have a joint model on parameters and data. And as far as we are concerned, they're just random quantities, and they're jointly distributed, and we have a probability model on them. That marginal on the parameters that we use to augment the model, that is known as the prior, because that is the probability distribution, the unknown parameters before you see the data. And multiplying that with the likelihood gives the joint model. And once you have a joint model, everything else flows from it. In particular, the joint model implies the conditional of P of theta given Y, which is known as the posterior. And you can make very basic arguments that everything you need to know about the unknown parameters, all the information is contained in that conditional distribution. And we can summarize the conditional distribution. Many times the theta might be high dimensional, so you cannot plot it, you want to summarize it. For example, you might want to report a point estimate. An appropriate point estimate might just be the expectation of theta under this conditional distribution. It's also known as the posterior mean. We might just write theta hat. Similarly, if you're interested in some function of the parameter, like in our previous example, an obvious function might be the pi sub d of theta, like the probability of treatment response at dose d. Well, again, you just simply take that function of interest and you report the expectation with respect to the posterior distribution on the parameters. So in a nutshell, that's what Bayesian statistics is about. Same thing again, a bit in more detail in a simple example. Let's assume we have a parameter with a prior, say the theta is like a parameter that lives on the unit interval. We might, for example, use a beta prior, a beta distribution, and it looks like what you see there on the right side. Then we add the data. Adding the data means we record the likelihood. For example, this could be a simple binomial likelihood. It's actually simpler now than the model that we had before, because now the theta is the success probability itself, rather than just indexing a function that represents a success probability. So the likelihood L of theta is simply the sampling model when you read it as a function of the parameter. What you see now on the right side, you see the original prior. The original prior was centered somewhere around 0.5 plus minus 0.2. The likelihood when we look at the evidence from the data, that seems to be centered around 0.8 or something like that. And now we simply use basic probability calculus. We can combine the prior and the likelihood to get the joint distribution. From the joint distribution, we get the posterior, which is down here indicated as P of theta given Y. And just basic probability calculus that nobody would argue with. Basic probability calculus tells us what we need to do, just multiply the prior times the likelihood. That gives the posterior. And you can beautifully see how, here was the prior, here was the likelihood. And you can see how the posterior is beautifully a compromise between the two. In plain English, what has happened was we do a shrinkage of the likelihood towards the prior, and using the rules of probability calculus, that is what we should report in the end. There was, in this case, there's something funny happening. When we multiply the beta prior with the binomial likelihood, what you get, you again get the kernel that again you can recognize as again a beta distribution, now with updated parameters. So all what happens is the posterior distribution is again a beta distribution like the prior was, but with parameters that are slightly updated. That's a very special situation. This is a situation where the prior and the posterior both live in the same family. Such setups are known as conjugate models because they're just analytically very convenient. Yeah, they're actually quite common. So just to record the same one again that we just saw. Sorry, the first part, you can see just a summary of it we just did now. Binomial likelihood, beta prior gives a beta posterior. And there are many more like this. Here's another common one. If you have a normal sampling model and the normal prior on the unknown normal location parameter, turns out the posterior on the unknown normal location parameter is again a normal distribution. So prior and posterior live in the same family. And there are many, many more. I don't want to go down the long list. I just want to point out a few more items of terminology. Many times the parameter vector is high dimensional, and we might be interested in one parameter in particular, say here the orange theta 1. For example, if this was a normal linear regression, we might have intercept and slope A and B and residual variance sigma square, and we might want to focus on the intercept and slope. Then we might want to report the conditional posterior, like the conditional of the orange parameter given the remaining black parameters, the way how it is written here. And that is known as the conditional posterior distribution. Or we might want to report the marginal posterior distribution. That means rather than conditioning, so what we are doing here is we are conditioning on values of the other parameters. Rather than conditioning on them, we might want to remove them by integrating out, and we're reporting the marginal posterior on the parameters of interest. Another distribution that's often of interest is when you start with the joint model, you can always integrate out the parameter, and then you're left with the marginal distribution for the data. That is essentially what you think where the data should come from. So this is known as the marginal distribution of the data. Footnote, the marginal distribution is actually what one should use to compare models. See here you can see marginal distributions under two competing models. And you should look at the ratio of these two to decide which model you should recommend. Notational footnote. All through this discussion, I'll use little p. I'll use little p as a generic notation for a probability model, for a probability density or probabilities. And most of the time I'll get away with that. Yeah, I'll just heavily overload the little p for just about everything. Occasionally I don't get away with it, and I'll start to use sub-indices to indicate what exactly I mean. One more piece of terminology we should mention, the posterior predictive distribution. That becomes meaningful in the context of IID data. So when we have IID data, assume that our data points yi are equal 1 to n. IID samples from some assumed sampling model P of yi given theta. Then the question arises, given the first n observations, can we predict the n plus first one? And that distribution is known as the posterior predictive distribution. The posterior predictive distribution is simply the sampling model for the next guy when you marginalize with respect to the posterior distribution on the unknown parameter. That is known as the posterior predictive. And maybe that's all I wanted to tell you about a quick review of Bayesian inference. If this was the first time ever you heard about it, it was way too fast. Trust me, it's really not difficult. In the end, it's just basic probability calculus consistently applied. There's a few more comments I want to make, in particular about posterior integration. So in the previous few slides, I very fast went through a basic argument of how a Bayesian would go about statistical inference. And let me repeat it again in slightly different words. So you can argue that in Bayesian inference, just about all statistical inference in the end boils down to reporting integrals of some red thing of interest with respect to the posterior distribution. For example, if you want to report a point estimate, if you're concerned about the point estimate of some unknown parameter theta, a reasonable thing to do is just plug in for the red thing, for the red integrand up there, plug in the theta itself, then we're getting the posterior mean, right? And we're getting theta bar, which is then just the integral of theta, p of theta given by d theta. Then we get the posterior mean. Prediction also takes exactly that form. We did it very fast on the last slide. But if you look, did you notice there was exactly that integral? There was the integral of p of the next observation. Sorry, it was y before, now it's suddenly x for no good reason, yeah? P of the next observation given theta, and then integrating with respect to the posterior on the unknown parameter. given the observed data d theta. That is the posterior predictive, and that you might want to use for prediction. For posterior probabilities, for example, if you want to report the probability of theta being beyond some threshold, you would just plug in the integrand indicator for theta being beyond that threshold. And you can keep on going on that list. You can make an argument that just about any statistical inference under Bayesian paradigm, any kind of statistical analysis takes the form of evaluating integrals of this type. So now the problem of implementing Bayesian inference has become a problem of evaluating integrals of something, the red thing, with respect to the posterior. And the problem is that that integral will rarely be of a form that you can solve it analytically. So we'll need some numerical or simulation-based methods. So it's rarely analytically solvable. However, it's not difficult either, because typically that f of theta is not an arbitrarily complicated or irregular function. It's usually something very well behaved. You can also make an argument that the integrating measure, in our case, the posterior distribution, that is usually something very nice. You can actually make asymptotic arguments. It should be something that asymptotically is approximately a multivariate normal. So integrating something well behaved with respect to a multivariate normal integrating measure is not in itself a very difficult or challenging numerical problem, but still we have to somehow solve it. I already did one thing here. Instead of spelling out the posterior as p of theta given y, I just skipped writing the given y, because we'll always condition on data. So we'll just write p of theta from now on in the short discussion of posterior simulation. One complication though is that the theta with respect to which we integrate, the parameter vector could be very high dimensional. Even in modest statistical inference problems, this could easily be, could be a couple hundred dimensions if you have some spatial temporal problem. Or if there's random effects, this could very quickly be high dimensional. So here's a very simple idea of carrying out it, of evaluating those kinds of integrals. So here's again on the left-hand side, you can again see, sloppily speaking, circled in red is Bayesian inference. Bayesian inference is about evaluating such integrals with respect to the posterior. See, here for the posterior, I still leave some space in memoriam of conditioning on y. But from now on, I'll just talk about integrating with respect to some distribution, which in Bayesian inference would be the posterior distribution. Well, if you recognize the left-hand side here simply as the expectation of f of theta in the expectation of f of theta under the blue probability model, then we could always approximate that. We could always approximate that population average on the left side by a sample average on the right side, where the theta i's are ID samples from that blue distribution P of theta. So at this moment, we have changed the integration problem to a simulation problem. We can evaluate that sample average on the right-hand side if we can draw an IID sample from the posterior distribution. And if we can do that by computer simulation, we can simulate as many as we want, and then by the strong law of large numbers, we would really get an estimate of the desired integral on the left side. Now, that doesn't solve anything, because all what we have done is we have replaced the integration problem. We have replaced the integration problem by another problem. We have replaced it by the problem of efficient random variate generation. If the posterior is not something well known and easy to recognize, it's probably not so easy to generate by computer simulation random draws from the blue distribution. So it really hasn't solved anything. It has just changed the problem. However, there's one nice thing. There's one nice little trick. It's actually not critical that this be IID. They could be dependent, the theta i's. You can allow dependence. So independence of the theta i's for that sample average, should still say that sample average on the right-hand side. That's also known as the Monte Carlo estimate. the sample average of the Monte Carlo estimate need not be based on an independent Monte Carlo sample. That is not necessary. Short of independence, the simplest form of dependence I can think of is by a Markov chain. So if we could construct a Markov chain, with limiting distribution that P of theta, the desired integrating measure, then again we would be in business. Like if we could construct an ergodic Markov chain that converges to the posterior distribution, we again would be in business. So now the problem has become, how do we find such a Markov chain? And fortunately, that is very easy, and that's the last thing I want to tell you about posterior simulation. Here's a very easy generic trick of how to generate such a Markov chain, and I'm sure many of you have seen it before. It's a constructive algorithm. So start having a current value of the parameter vector, being a Markov chain. All what I owe to tell you, I have to tell you how do we get the next one. Let's note this one is theta super t. I have to tell you how to get theta super t plus 1, right? If the theta t is a p-dimensional parameter vector, let's call the coordinates a1 through ap. Then here's how you move from theta super t to the next one, theta super t plus 1. Operate like what's coming up now is a definition of the transition probability by a generative model. What we do is we first replace the first coordinate by a draw from, can you recognize this guy on the right side? Can you recognize this as the conditional posterior distribution of the first parameter given the remaining parameters? Then we've replaced the second parameter by a draw of the second parameter from the conditional posterior given the second parameter given all the other parameters and so on down to the last one. And now we have all the new parameters. So these are then all the new parameters which I had marked there in blue. So it's now simply in blue A1, A2, all the way down to AP. And that is our new parameter vector, and we have defined a transition probability. That is very attractive. So in our upcoming discussion of non-parametric Bayes, we'll occasionally talk about conditional posterior distributions. The reason why we'll talk about conditional posterior distributions is if you know the conditional posterior distributions for one parameter given all the others, that's all you need to know to implement inference, because then you can set up this Markov chain. This Markov chain is known as the Gibbs sampler. You can set up a Gibbs sampler, this algorithm, and that way you can always approximate posterior integrals of any function of interest by Monte Carlo samples with respect to the simulated Markov chain. That's the reason why in the upcoming discussion we'll often talk about the conditional posterior of one parameter given all the other parameters and the data. I didn't write the conditioning on the data anymore because it happens all the time. Oh, and I should still say these univariate conditional draws, we can always make them because generating from a univariate distribution, that you can always do. If nothing else, I assume many of you speak R. You can just sample from a grid-based evaluation of the distribution. You can always generate univariate distributions. And last slide of our little review here. This is just an example of if it's a bivariate thing. So here is theta 1, here is theta 2. Of course, if you really had a bivariate posterior distribution, you probably would not bother running an MCMC. Did I mention that the Gibbs sampler is just one of many similar algorithms that are generically known as Markov chain Monte Carlo, MCMC. So if you really had only a bivariate posterior distribution, you wouldn't really bother with running a Gibbs sampler or more general MCMC, because bivariate integration is reasonably easy to do numerically. But if you did it, then you would see, can you see these typical horizontal and vertical draws? Like each of the vertical draws is simply when we draw from P of theta 2 given theta 1. And each of the horizontal draws, like for example, this horizontal draw, we have just replaced theta 1 by a draw from the complete conditional posterior of theta 1 given theta 2. And iterating over these is what the previous algorithm defined. So this was, that's it. That's what I wanted to tell you by way of review of Bayesian inference and posterior integration. And again, if it was the first time you heard it, it was way too fast. If you've heard it many times before, then it just reviewed notation and terminology a little bit. I promise it's not difficult. Here are just two references that you can access for free. Peter Hoff's book is a nice little book, includes lots of little R fragments, and you can get it in the McGill library for free. And the other one is another little book that you can get for free as a PDF. So that's all I wanted to tell you about Bayesian inference in general. Maybe that's a good moment to stop. Any general questions about Bayesian inference or MCMC, or are we ready for non-parametric Bayes? I'm looking at no chats, no complaints, no comments. How about, like, can you guys all understand me? Like, should I'll talk anyway slower now as we talk about non-parametric Bayes, yeah? If you cannot understand me, then please just unmute and ask, because chances are, if one of you doesn't understand me, many don't, and just as well I repeat it, yeah?
Peter, just so you know, I'm following the chat window and I'm managing here, so. But
so you will tell me if there's something coming up, right?
Yeah, so, definitely.
So I hope I didn't bore you too much with that high-speed review of Bayesian inference, but just making sure we're all on the same page. So if you downloaded the slides from that site that's here in orange, the slides are organized in 4 parts, and we'll just go like essentially one part at the kind of, and the 4th part is if we have extra time on Wednesday. So we're now talking about part 1, density estimation. I think of density estimation kind of the easiest statistical inference problem. Like density estimation is essentially when you have data yi come from some distribution f, and we want to make inference on that f. Say that f is unknown, and we want to make inference about the f. That is density estimation, right? Under Bayesian inference, if you have an unknown quantity there, then what we need to do is like this first line, this defines P of y given the f. To carry out Bayesian inference, I have to complete the probability model. Like that first line is the sampling model that gives P of y given f. I would have to complete the probability model by assuming a marginal distribution on the unknown f. The two of them together define a joint distribution, and I can go from there. This here is the prior on the unknown distribution. If you're willing to assume that the unknown distribution lives in the family of normal distributions that is indexed with location and scale. So if you're willing to assume that f is just in some parametric family, like normal, location, and scale family, then it just reduces to a parametric statistical inference problem. So if that theta here is say in the RP with location and scale, it would just be the R2, right? Then it's just a parametric inference problem, and like then we are back to parametric Bayes, which we just talked about briefly and very fast. But it gets interesting. In some problems, in some problems, it is inappropriate to make this assumption. If it's inappropriate to make this assumption, if we don't want to assume a parametric family. For example, there on the left slide, see, if I assume a parametric family, if we assume a parametric family, then the extrapolation here is almost deterministic. There's very little uncertainty. On the right slide, it's even more difficult. If you assume a parametric family like a bivariate normal, then you're really losing most of the detail that's going on here, right? So there are many situations where assuming a parametric family is inappropriate. Then we need P of f, where the f is just a distribution. That's an awfully big space. You can't index it anymore with finitely many parameters. Then we need a prior on the unknown distribution, and that would become a BNP, a non-parametric Bayes prior. Don't ask me why BMP has become common as an acronym for non-parametric Bayes. Non-parametric Bayes, I would have said NPB, but it has become customary to abbreviate it as BMP, Bayesian non-parametrics. So in the next few slides, I want to talk about prior probability models for unknown distributions. And at the beginning, initially, it might seem like an intimidating thing because that unknown distribution F in general could live in an arbitrary space. But it actually turns out to be much easier once we get down to actually doing it. There was a question, does it necessarily have to live on an infinite dimensional space? Quick answer, yes. Because if you're willing that the F lives in a space that is indexed by finitely many parameters, then it's parametric Bayes. That said, practically, you can approximate non-parametric inference by a mixture of free normals. If you take a mixture of free normal distributions, you already can get many things. Like here, a mixture of free normals, I think, would probably capture most of what's going on here. And the mixture of free normals is finite parametric. So pointed answer to the question, does it always have to be an infinite dimensional space? Pointed answer, yes. However, using a finite dimensional model, you can probably approximate it very well. Yeah? So that's what we are going to talk about, such priors. And here comes the first one, the most beautiful of all, the Dirichlet process. To introduce it, let me just start with a little example. So here's an example. This example is about the data kept T sub I. T sub I is the time it takes to repair a leak in the lung of, like, these are patients who underwent some lung surgery. They underwent some surgery in the lungs, and it can happen that part of the surgery, a leak could arise. I think of that like kind of like a leak in my bicycle tire. It's kind of scary, yeah? But so it happens that these patients can have a leak in their lungs, and T sub I is the time it takes until the leak resolves. Of course, the sooner it resolves, the better. And there's two competing treatments we are comparing. Apologies, most of my examples will be kind of biostat or bioinformatics-like, because Alex comes from you're in a biostatistics department, right? Or epidemiology. That's the reason. No, it's simply the examples that I happen to know. So we want to compare these two treatments and let the better one win. Now, there's a little twist to that. Just reducing the TI, just reducing the average TI is actually not enough to show. What's really going on is reducing the TI by just 1 day in the early days is much more important than reducing it by 1 day in the late days. Whether it takes 44 days or 45 days almost doesn't matter. Whether it takes 1 or 2 days makes a huge difference clinically. So details of the distribution matter, not just the mean. And maybe that's best to show in the, let me quickly jump ahead and show you that little picture here. In that little picture, you see in black we have the, let's denote with G0. G0 is the distribution of resolution times distribution of the TIs under standard care. And in red, the G1 is the distribution under the experimental therapy. If you were the patient, you would probably by far prefer G1 because you see that G1 has an atom here at 0. That atom at 0 means you go home immediately. You don't have to stay in the hospital. That means the air leak does not even arise, or it clears immediately. So although the mean, the red mean and the black mean might not be that different because the red one only took that probability mass here from G0 and moved it to the atom at 0. But the implication for the patient is huge. So in this example, it's important that we understand the subtleties of the unknown distributions of the TIs, because if we just go after the mean, we totally miss what's going on here clinically. So let me go back. I'll go back again one slide, just to introduce the notation G0 and G1, although I already said in words. So we'll denote with G0 That's the distribution of event times under standard care. So this is the distribution of time to resolution of the air leak under standard care. And in red is the G1. That's a distribution of the TI under the experimental therapy. The treatment is called ProGel. It's some kind of gel that you smear into your lungs, and that helps to resolve the air leaks. If you were to use a parametric model to represent the G0 and G1, we will probably miss the point. So instead of a parametric model, we want to have a BMP prior for the red G1 and the black G0. And then there's just a footnote about statistical inference, not so much about BMP itself. What you should really do here to compare them, you should probably elicit preferences for patients, like what you see here in the second panel here shows patient preferences for different times. Can you see the change from 0 to 1 day for waiting for a resolution is huge? Whereas the change down here, you see the change from, is it from 35 to 40? There's a minuscule change, just like this mini change. Whereas here is that huge change, yeah? This one here is way bigger than that change in utility. I care a lot whether I have to stay 1 or 2 days in the hospital. I don't care so much whether it's 35 or 36 days. And what you should do is, then you should simply see the, call these preferences, call them utility. Then the average utility becomes the V bar in the far right, and let the bigger one win. That's the one you should recommend. Don't want to dwell too much on the example. It's, I think, a very nice example by itself too. Just wanted to bring this as a motivation for to make this example work. We need a probability model, we need a P of G1, and we need a P of G0. And in short, what we'll assume that this comes from a so-called Dirichlet process prior, and that's what we'll talk about now. It's probably the easiest of all, the Dirichlet process. So the Dirichlet process is the most popular of all BMP priors, I think. One of the reasons, probably the simple reason is it turns out to be computationally really simple to handle the Dirichlet process prior. It goes back all the way to 1973. So we say that an unknown probability distribution, let's call it F here. We say that an unknown probability distribution F arises from a Dirichlet process if the following thing holds. And let me first show it in the right side here in a picture. In a picture, what we want to do is I want to generate my random F the following way. And we'll spell it out in the slide in a second, yeah. Here comes my random F. This is my desired sample space for the F, let's call it X. What I shall do is, first I generate random locations for atoms, say here, 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 here. Let's give names to the atoms, let's call them M1, M2, M3, M4, M5, and so on. And then for each atom, I'll generate a random probability mass, say that much here, that much here, that much here, here, and here. Let's give names to these probability masses. Let's call them P sub 2, then this becomes P sub 1, etc. Then the sum of these discrete probability masses, that becomes my F. That's it. So going back to the formal definition, here's the F. The F is just the sum of the sticks on the right side. In writing the F like this, I've already made a statement. I've already made an important statement here. The Dirichlet process prior obviously generates with probability 1 discrete probability measures, means probability measures with atoms, because I can write it as a sum of these atoms. The delta MH just indicates a point mass at location MH. And it's infinitely many of them. Although it's infinitely many of them, of course, still the probability mass has to add up to 1, right? The P sub H has to add up to 1. So now life has become much easier. Writing it like this, all by the O, you know, is I have to tell you how we generate the locations of the atoms. And I have to tell you how we generate the actual weights, the probability weights that go there. And that's where it becomes embarrassingly simple. The formal definition is coming up down there, but let me tell you in words also on the other side. So the M sub H, that's as simple as it possibly gets. We simply draw them IID from some probability distribution, let's say F star. So the locations of the atoms is just IID from some base measure F star. The F star we call the base measure. And the P sub H, I cannot ask for them to be IID because they have to add up to 1. For the P sub H, we do the following construction. We look at the total probability mass of 1. And we'll first break a little fraction, let's call it V sub 1. And that becomes my P1. Where the V sub 1 is a draw from a beta 1M. This just draws a little fraction that I use for the first weight. From what remains, draw again a fraction, say V2, and that becomes my P2. So the V2 is again a beta 1M, and so on. And that generates then, there's like we keep on generating these little fractions, and that generates the desired probability masses. So for example, here, did you see the P2 is a fraction V2 of what was left? What was left here? What was left here is 1 minus P1, right? Or in general, you can see the definition on the left side in the little box. It's a two-line constructive definition of the Dirichlet process prior. It's a discrete probability measure where we draw the locations of the atoms IID from some base measure and the actual probability masses that we allocated those locations. We get them by this construction. This construction has a name. It's called stick breaking because you can think of starting with a stick of length 1, and then we just iteratively draw fraction. We just break off fraction, better distributed fraction from that stick, right? So that is a constructive definition of a random probability measure. It's our first BMP prior. In that construction, if you paid attention at construction, I needed 2 parameters. I needed to specify the probability of the base measure from which we take the IID draws of the locations, and I have to specify the parameters of the beta distribution. So these are the 2 parameters that characterize the Dirichlet process prior. You can almost, you can think that what I wrote there on the right-hand side, or the 2 lines in the box, you can write a few lines of R code to generate random probability measures now, just following these 2 lines. So for one, the representation is very easy and elegant. And another reason why the Dirichlet process is so popular is posterior updating is also as easy as it gets. Well, I should be more specific. Under IID draws, so if you have like a density estimation problem, if the likelihood is that we are drawing Y from F, when we are drawing Y from F, that means P of Y given F is simply F of Y. Looks a bit funny, but that's exactly what it means when you draw the Y from the unknown distribution F. And our prior on the F is the Dirichlet process prior that we just talked through. Then it turns out that this is a conjugate pair, like IID sampling, and the Dirichlet process prior is a conjugate pair of likelihood and prior, because it turns out the posterior distribution is again a Dirichlet process. And all what happens is we have to update the parameters of the Dirichlet process, the total mass. Did I say that cap M is also known as the total mass? This guy here is known as the total mass. The cap M is incremented by 1. That's exactly why it's called the total mass, because the cap M has something like an interpretation of prior equivalent total sample size. And the base measure the base measure is updated by what you do is you start with the original base measure and you essentially add just a point mass. You essentially add the empirical distribution. I have spelled it out here for a single sample from the distribution. If instead these were multiple samples, if these were like yi I equal 1 to n, then we would have updated by adding here n, and here we would add plus, let's say, note with f hat the empirical distribution. Sorry, my mistake, I goofed. I should replace this one here by a sum I equal 1 to n of point mass at the yi, which is almost the empirical distribution except for scaling by 1 over n. So posterior updating is damn easy. It's easy to characterize it. It's easy to understand it. That's one of the reasons why the Dirichlet process is so popular. On the next slide, I just show you on the left slide, these are just draws from the Dirichlet process. Oh, showing random. So what I want to do is I want to show when I draw f from a Dirichlet process prior with some m. I think my m was 1. And some base measure. I think my base measure was just a standard normal. I just want to show you random draws. Now, showing you random draws, showing the probability mass function would look super ugly because it's just a mass. It's much easier, it's much nicer to show it at the level of the CDF because here is the standard normal CDF, that thick line, that's the F star. And the gray spaghetti that you see around it, the gray spaghetti, those are the CDFs of random draws of probability distributions F from the Dirichlet process. They're all discrete, so their CDFs have to be step functions. But those step functions are in some sense centered around the continuous normal CDF. So all these are random draws F. This here is a random F generated from the Dirichlet process prior. And that would, if this was the prior, then what you see on the right side, do you see the little pins here at the bottom? Those are yi's, say yi from f. So we have a density estimation problem. And then what we want to report is we want to report the posterior distribution on f conditional on the data. The posterior distribution on f conditional on the data is again a Dirichlet process. Where it's now updated. See this, the bold line here, that's the F1 star. The F1 star is M F0 star plus summation of point masses at the data points, summation of delta yi. Is everyone comfortable with the notation of delta x for a unit point mass at location x? Then summation delta yi becomes the empirical distribution scaled by n. Can you see the bold face shows now the F1 star, the posterior mean of the unknown distribution, and the gray spaghetti show the uncertainty around it. And that makes total sense because see down here's the data. Like the prior was centered around, the prior of the unknown distribution was centered around 0. The prior was centered around here. And can you see how the observed data? The observed data moved it prior, shifted it quite a bit to the right as it should be. So one of the reasons, like the Dirichlet process is the most beautiful of all. It's super easy to characterize. It is easy to do posterior updating. There's no problem. The only problem is it's ugly. It's just not beautiful. I really cheated here in this picture by showing you the CDF. If I had showed you the probability mass function, it would look really ugly. Yes?
We have a question in the chat. How important is the choice of base measure?
Thank you, good question. Depends on your sample size. If the sample size is large enough, it becomes increasingly less important. So pointed answer to the good question. Yeah, pointed answer to the question. Can you stare at this line here? I'll just copy it there to the right. It's a good question. Yeah? I'll copy it there to the right side. The F1 star is equal to m times the original base measure plus summation I equal 1 to n of delta yi. I could rewrite this here as n times f hat. The f hat is just the empirical distribution. Let's call it f hat sub n for the empirical distribution of n data points. Can you see now? Now it's kind of staring in your face. If the n is large, if the n is much bigger than m, then my pointed answer would be it's not important. If the n is moderate or small, then it could be important. So it depends a little bit on the sample size and other things. But back to our Dirichlet process. The Dirichlet process is ugly because it's discrete. Next thing we want to do is, so I'll draw here again a picture of my Dirichlet process random measure. So here's my Dirichlet process random measure. Ugly as hell, like you don't really want to show something like this is your inference, right? This is my Dirichlet process random measure f. We say we are in a situation where we don't like inference. We don't like to report a discrete distribution as our inference. It just doesn't look good. There's a very simple fix. We can easily make the discrete distribution into something continuous by convoluting with, just convolute with some continuous kernel. Like smear out each of these point masses with a little Gaussian kernel. If you do that, then instead of the sum of the point masses, you get a beautiful distribution like this. Let's call it G, where the G is now just the integral of that kernel. Say if that kernel, we might use, for example, a normal kernel. If we use a normal kernel centered at mu variance sigma square, then we integrate with respect to the discrete prior on df of mu. If the f is discrete, if the f is just a summation of the point masses, if that f is discrete, if it's summation h equal 1 to infinity of p sub h times a point mass at m sub h, then this integral is just a complicated way of writing summation h equal 1 to infinity of p sub h times a normal centered at m sub h with variance. We assume that's fixed. And that's all what it boils down to. Or in other words, if you don't like the discrete black distribution, it's easy to make it beautiful continuous by smearing out each of the discrete probability atoms, smear it out with a Gaussian kernel, then you get a nice mixture of normals, and that looks beautiful. And that's exactly the idea of Dirichlet process mixtures, which appears now on the slide on the left side. So if we take our, here's again the ugly discrete f of y. So this f, this is the summation of the point masses at atoms m sub h. If we smear it out with that red continuous kernel, obviously need not be a normal kernel, but without loss of generality, let's assume a normal kernel, then we get a beautiful continuous distribution, and this is known as the Dirichlet process mixture. These are very popular models because Dirichlet process mixture, do you get the flavor? It's essentially a systematic way of using mixture of normal models. So it's essentially a mixture of normal models. Here's a typical example. Let's not get stuck with the details here. On the left side, you see the data. So this here is simply the data. These here are the y sub i's. That histogram, the histogram essentially is the f hat sub n, right? The histogram essentially shows you the empirical distribution of the data. It's just the data. And on the right side, you see our first for reference. You see the dashed yellow line. This is just an estimate of the unknown distribution as a kernel density estimate. Which looks pretty beautiful and nice. The gray line, that's our estimate using a Dirichlet process mixture of normals. Let's call it G bar. So the Dirichlet process mixture of normals implies a posterior distribution on the G, and G bar is just the posterior mean. And the spaghetti that you see, the spaghetti, those are just draws from the posterior. So these are G from the posterior on G given the data. What you can see here already is two typical observations. Can you see that the BMP estimate of the unknown distribution, should have probably gone slow and pointed out, our statistical inference model here is a typical density estimation problem. We assume that the YI from some unknown G, where the prior for the unknown G is a Dirichlet process mixture, as on the previous slide. What you see on the right panel, you see our posterior inference. And there's two typical observations. Turns out the posterior mean, if all what you want to report is a point estimate for the unknown distribution, that's the thick gray line. We really did not need the big machine of BMP because the thick gray line would have looked just as well, could have been just as well the dashed yellow line, which is a simple kernel density estimate. So if all what you need is a point estimate of an unknown distribution, you probably don't need BMP. However, if uncertainty about the unknown distribution is important, if you need the full posterior distribution, maybe because you want to make a judgment on which treatment is better for which you need the uncertainties, then the BMP becomes interesting because you get the spaghettis. Same thing sloppily as a one-liner. The added value of BMP inference for the density estimation is not so much the point estimate of the unknown density. It is really the principled report of uncertainties, like you get a full posterior distribution on the unknown G. And it's the spaghettis here, and it's simply the posterior on the G in a Dirichlet process mixture. Now, did you notice something? I think nobody asked. Did you notice something? In the previous slide, when we talked about the Dirichlet process prior, I celebrated in all glorious detail what the posterior distribution looks like. Now, when we talk about the more beautiful Dirichlet process mixture, I just stated the Dirichlet process mixture. I said it generates beautiful distributions like mixtures of normals, and I glossed over the posterior thing, posterior inference. There's a simple reason. You can't do closed form posterior inference anymore. So it's not that straightforward. That's why we didn't talk about it. But it's still totally doable. However, it becomes totally straightforward with a simple trick. Like if you're familiar with Bayesian inference, if you have worked with mixture models before, and what we have there is just a mixture model. Can you see our model for the unknown distribution is simply a mixture of normal. When you have a mixture model, you're probably itching to replace the mixture by a hierarchical model in a model augmentation, and then it's typically easier to implement MCMC. That's exactly what we'll do now. So same thing, more formally said. To talk about posterior inference, what we are going to do is we are going to replace what you can see here again is, this again is the Dirichlet process mixture model, DPM. Sorry, it's just sloppily stating the Dirichlet process mixture model. I should have included there F, like the prior on F. The prior on, what was that? I have no clue where that thing came from. The prior on F is, it comes from a Dirichlet process with some total mass and some base measure. The two of them together specify a Dirichlet process mixture model, right? If you replace the mixture, if you replace this mixture here by a two-liner, and if you have worked with mixture models before, that's kind of a natural thing to try. Augment the model. Yeah, but all what we are doing here is we are augmenting the model with latent red parameters theta I. So we are adding these latent theta i's, where we say yi given theta I comes from the normal kernel. So in here we're thinking of a normal kernel. And the theta I comes from the integrating measure f. The two of them together are totally equivalent to the line above, because when you try to marginalize with respect to the red latent variable, you would integrate the product of the two lines, and integrating the product of the two lines, you're exactly back to the line on top. Once you write it like a hierarchical model as this two-liner, it becomes much easier to talk about posterior inference. First, there's an important observation, and that observation might seem like a footnote, but it will turn out to drive a lot of applications of Dirichlet process mixtures. Can you see what's going on here in the second line? That second line is kind of says a funny thing. The F, remember the F is a random probability measure generated by a Dirichlet process, which means in particular that it is discrete. So the F is just a summation of atoms, h equal 1 to infinity of p sub h times a point mass at m sub h. The theta I, the latent theta I, draws from a discrete probability distribution. When you have a sample from a discrete distribution with positive probability, you will get some ties, right? Like when you sample from a discrete distribution, some of your samples might be identical. You will see ties. Or in general, when we take here n draws, say we are taking n equal, how much was it in our previous example? We had 51 draws. So when we have here n equal 51 draws, then many of those 51 theta i's might actually be tied. There might be a much smaller number of identical ones. Can you please cheat 1 second? I'll just quickly look back to that picture. Looking back to that picture, I think there's probably something like 4 or 5 unique ones. See, there might be only 5 unique values. So of all those 51 theta i's that are introduced here, only 5 of them are different. Let's call them theta 1 star through theta 5 star. See what I did when I eyeballed it quickly. See what I did was the full Dirichlet process mixture model is a mixture of infinitely many normal kernels, right? But when I stare at that right picture here, when I stare at the spaghettis, most of these spaghettis, they look like a mixture of maybe 4 or 5 or 6 kernels. That's what I was looking at. I was staring at these, like if you stare, for example, let's pick out any one of them. So here, staring at this one, I see like a mixture of 4 normals. And that mixture of 4 normals, maybe here could be theta 1 star, here could be theta 2 star, here could be theta 3 star, and here could be theta 4 star. Like I really only see a mixture of 4 distinct normal kernels, although in general it could be infinitely many. But so of the theta i's, of the latent theta i's that we introduced here, maybe there's only 5 distinct ones. Let's call them the theta 1 star through theta 5 star, the purple theta stars that they had, that I just indicated sloppily on the previous figure. So that's just an observation. That's just a consequence of the discrete nature of the random probability measure. We can do one more thing. See, if we recognize that there's really only a mixture of 5 normals going on, if there's really only a mixture of 5 normals going on, can I still, in the right figure, I should have actually indicated the data again. Can I just add the data? I'll edit the data here as like little pins. The data was, there were some observations here. I'm just trying to copy the histogram on the right side. There were lots of observations here, and then again a cluster here and so on. So those little guys down here, those are just the data, those are the YIs. Can you see how these unique theta star, they introduce clusters of the YIs? Because some of them might just belong to the orange theta 1 star. Some of them might belong to the green theta 2 star. Some of them might belong to the red theta 3 star. And some of them might belong to the blue theta 4 star. That introduces clusters, or more formally here in the next slide. If I look at the latent theta i's, some of the theta i's will be matched with the blue theta, I think it was theta 4 star. Some of them will be matched with the orange theta 1 star, and some of them will be tied with the, I think it was the green theta 2 star, etc. So that creates clusters, that implicitly creates clusters of the theta i's. And we can introduce latent cluster membership indicators set I. So that set I would say, what was the green guy? In my picture up there, the green guy was 2. So set I is 2 if the latent theta I is equal to the unique theta 2 star. The set I is equal 1 if we have a tie with the theta 1 star. The set I is equal to 4 if we have a tie with the blue theta 4 star, and so on. Can you see how the discrete nature of the random probability measure induces a partition of the data? It induces a partition of my experimental units into, in this case, orange, blue, green, and red. Or in general, it induces a partition of the experimental units into clusters that are characterized by ties with a small number of unique values. So what seems like just an offhanded description and a minor consequence of sampling from a discrete distribution, it's actually one of the main uses of the Dirichlet process mixture models. Like one of the things is that the silly color coding that I introduced here, you realize that this color coding means the partition of the data points is actually random. Like the probability model implies a probability distribution on that random partition of my experimental units into different color subclusters. If the experimental units, in this particular case, the experimental units were actually patients, because those were samples from breast cancer patients, I think. Yeah? If the experimental units are patients, then this random partition of my experimental units into different color clusters essentially describes a probability model for a random partition of your patients into interesting subpopulations. And that is often useful if you can understand if you can understand about subpopulations of your patients. So back to our Dirichlet process mixture model that includes a probability model on random partitions that we shall still use quite extensively. And it actually turns out that implied partition that arises from these ties with the unique values, that actually is very easy to describe. So on the next slide comes now a formal description of this implied partition. And that's one more reason why the Dirichlet process is so popular as a model. Yeah. This first item just summarizes what we just talked through in the last slide. That when you rewrite the mixture with respect to the Dirichlet process random measure, when you rewrite the mixture as a hierarchical model with latent indicators, then ties of those latent indicators induce clusters, and we get a probability model on random partition of the data. That is nice to know, but it's useless unless you get like a nice description of the probabilities, and that's where we run into some good luck. Yeah, that good luck, you see the bottom line of the good luck. You see down here. The bottom line of the good luck is, it turns out these cluster membership indicators, their distribution is very easy to describe. But let's just slowly get there now. I should have introduced here maybe before an extra line, P of theta given F. P of theta given F is very simple. Yeah. Let me flip back to the previous slide. If I flip back to the previous slide, see what's going on is the way how I did my model augmentation. The theta I are just an IID sample from F. So if you give me F, then the joint distribution of theta is very simple. If you give me F, then the joint distribution of theta, I have it here on the bottom of the screen. The joint distribution of the theta is simply product I equal 1 to n of F of theta I. That's the joint distribution of the theta if you give me the F. And the next line is asking now, what happens when you marginalize the F, when we try to marginalize with respect to the F. The prior on the F is the Dirichlet process prior. So the next line is asking what happens with the joint distribution on the theta's when you marginalize with respect to the posterior with respect to the Dirichlet process prior on the F. And that's where we run into some good luck. It turns out the distribution that you get is very simple. Now the first statement, it's actually always true. There is a joint distribution because those are jointly distributed random elements. The joint distribution, you can always write it as the marginal in first times the conditional of the second given the first and so on. Like you can always write the joint distribution of two guys. You can always write as the marginal of one times the conditional of the second given the first. And if it's not only two but n, then you get to that line here, right? Like if it's n of them, you just keep on going with this increasing conditionals. But we run into some good luck in that these conditionals, these increasing conditionals, they turn out to be of a very simple nature. And to make it even easier, instead of the increasing conditionals for the theta I, I'll just show you the increasing conditionals for the cluster membership indicators. Do you remember the definition of the set I? Let me flip back to the previous slide and quickly flip back to the previous slide. We introduced, here was the definition of the set I. Set I is equal J when the ith experimental unit is in a J.E.P cluster. So instead of telling you the joint for the theta, I can instead give you the joint for the cluster membership indicators. And I should have said here, and I have to tell you that the unique values, they are simply IID from the base measure. The base measure, I think we call it F star of theta J star. So instead of giving you the theta i's, I can just as well, I could either give you the theta i's, or I can equivalently give you the set and the unique values. Because if I tell you the unique value and I tell you who is tied with which one, I've given you the thetas. The distribution of the unique values is easy. They're simply IID from the base measure. That's because of, remember the very first slide on the Dirichlet process, we generated the location of the atoms by IID draws from the base measure. And the conditionals for these, so for these cluster membership indicators, it turns out the conditional of, can you read it as the conditional for the next guy, the conditional for the next guy joining the J.E.P cluster, the probability of the next guy joining the J.E.P cluster is simply proportional to, I didn't say what the NJ was. The NJ is simply, in plain English, it's the size of the J.E.P cluster. Formally, the size of the J.E.P cluster, I can write it as summation I equal 1 to n of indicator set I equal J. This is simply the size of the J.E.P cluster. So the next guy joins the J.E.P cluster with a probability that's proportional to the size of the J.E.P cluster, or it could go into a new cluster, means it's not tied with any of the earlier unique values, with a probability that's proportional to the total mass parameter. Now, that expression is not at all obvious, but it turns out it's true. And it's important enough, it has a name. It's known as the Pólya urn. So this is the Pólya urn. So bottom line now, we argued that sampling under Dirichlet process mixture model induces a probability model on a random partition. And it turns out the prior for the random partition is very easy to describe. It's actually characterized by this Pólya urn, which is the two-liner here. So one of the reasons why the Dirichlet process is so popular is because it induces a probability model on a random partition of experimental units, for example, clustering of patients. And that probability model is very easy to describe. It's the two-liner here. So for the, we'll still revisit clustering quite a bit on, I think plan is to do that on Wednesday. Yeah? So on Wednesday, we'll talk much more about inference on the random partition, because when you hear talks or read papers that use Dirichlet process mixtures, many times all what they are after is that random partition. So we'll talk about that at length on Wednesday. But as far as density estimation is concerned, for the moment, that's all I wanted to tell you about the Dirichlet process. And we are ready to move on to the next one. So ideally, I would like to talk today through 3 models for random probability measures. The Dirichlet process, we are done with that one. Then the next one already coming up on the bottom of the slide, the Pólya tree. And then still want to talk about normalized random measures. After I have half an hour, that might actually be enough because I don't have so many slides coming up. But this is actually a good moment to ask about Dirichlet process and Dirichlet process mixture. Warning, this was all a little fast, and like people build entire careers have been built on these Dirichlet process mixture models. We just quickly reviewed it, but we really talked about all the basic issues. One big can of worms is how to implement posterior simulation. We didn't talk much about that, simply because it would take us astray a little bit. So if there are no questions, I see no chat messages, then I would move on to the Pólya tree. So now it gets really easy. We'll talk, the Pólya tree is another prior for unknown probability measures. Like we're still talking about density estimation, means we're talking about priors for unknown probability measures. Now, a step back for a moment, forgetting all your statistics. If you just had to do a prior for a random probability measure, how would you do it? How about this? We can simply draw random histograms. Like here on the right side, I'll just talk you through a naive version of a random histogram. So I want the prior for a random probability measure on, to make it simple, let's say on the 0-1 interval, but it could really be any desired sample space, yeah? So to put a prior for a probability measure on the 0-1 interval, I could simply put a random histogram. Now the easiest histogram I can think of is I can split it into 2, and then I have simply a 2-bar histogram, yeah? Let's call the left side here B0 and B1. Then this would just be F of B0, and this would be F of B1. Well, of course, a histogram with 2 bars is not exciting, right? So you might want to refine it into a histogram with 4 bars. To refine it into a histogram with 4 bars, I might do something like this. Now it's a histogram with 4 bars. Let's call this here B00, B01, B10, and B11. I'm just giving names to the grid cells, yeah? When we refine the histogram, when we refine the 2-bin histogram to a 4-bin histogram, it's best to think about simply splitting the FB1 into what we need here is we need FB11 given, let's just say we have the height of the histogram is FB, I goofed, it's FB10, right? The height of this histogram here, this is FB01, and so on. And I could keep on going. We could split it finer, make an 8-bin histogram, and so on. And I could always move from the 4-bin histogram to the 8-bin histogram by splitting the bins of the 4-bin histogram, etc. And that's exactly what we'll do. And doing that is known as the Pólya, the Pólya tree prior. So the Pólya tree prior is essentially about random histograms, exactly the construction as I started doing it there on the slide on the right side. And if we keep on making it finer and finer in the end, we'll get a random distribution, right? Like if we keep on doing that forever, in the end, we have a random distribution. That's it. It's as simple as that. All I have to do is I have to tell you how I generate the random histograms, yeah? And that is so easy. It fits into the little box down there. So first of all, we introduce notation. We call it random histogram a Pólya tree. So this is the Pólya tree. Because I could have arranged my random histograms like on a tree, yeah? Start out with the 2 bins, then you split the 2 bins into the 4 bins, and the next level of the, sorry, it's an upside down tree. It's really a root, right? So we start out with FB0 and FB1, right? Then that gives us the 2-bin histogram. To get the 4-bin histogram, we need the random probability of B01 given B0. And here's the way how we generate the random probability of B01 given B0, which just generate from a beta random variable with parameters alpha 00, alpha 01. And in the same way, we keep on going. Anytime we have a beta, anytime we have a B sub epsilon, epsilon is not just a binary sequence. Sorry, can I redo that more beautifully? When we have a B sub epsilon, we split that B sub epsilon into B sub epsilon 0 and a B sub epsilon 1. And we keep on doing that recursively. And if you have f of B sub epsilon, then we generate f of the descendant subsets as f of B sub epsilon 0 given B sub epsilon. And to generate a random distribution, this becomes a random variable. Let's give a name to that. Let's call it y sub epsilon 0. And we draw it from a beta distribution with parameters alpha blah blah and alpha blah blah.
Peter, there is a question in the chat.
Let's see. Do we continue to split the bar for each split? None of the new bars can be greater than the previous bars. Sloppy answer, yes. More detailed. So the question was, when we split the histogram, when I split, initially I had, let me make in red, I make the 2-bar histogram. So in red is the 2-bar histogram, and then I move to the 3-bar histogram. And that's really all we need. Yeah? If you know how to move from red to black, then you also know how to move from black to blue, etc. Yeah? So the black histogram bar here, that's, for example, that is actually taller than the red one, but the probability mass is not bigger. Like all what we did was I split the red probability mass of B0, I split it into the probability masses of B00 and B01. So in the sense of the probability masses, the descendant histogram bins have to always add up to the parent histogram bin. They can certainly never be bigger. Although the histogram bar can be taller, like here, that one here ends up taller. Yeah? Actually, one of them has to be taller because if all of them were smaller, then they couldn't add up to the parent, right? So all what you need for that construction, I need to tell you how to split the, in the previous picture there, this would have been the red parent, and we split the red parent into the two descendant histogram bins, right? And you generate the descendant histogram bins. All what I need to tell you, I have to tell you the conditional probability. I mean, you multiply the conditional probability with the marginal probability, you get the probability of epsilon b epsilon 0, and we just generate them from beta distributions. So back to the left, back to the slide. We can define that infinite sequence of refined histograms. I can define that infinite sequence of random histograms just by drawing beta distributed conditional probabilities of going left and right. That's it. That's a very simple definition. In that definition, I made use of 2 sets of parameters. One parameter was the one set of hyperparameters, the parameters of these beta distributions for the conditional probabilities. So that's one parameter that I need. And the second set of parameters really are these partitioning subsets, like the B sub epsilon. That's the second set of parameters. In my little cartoon there on the right side, I cheated. I just took like halves and quarters and eighths, etc. Hoping that if I just take halves and quarters and eighths, nobody will ask me. In general, though, it's a choice you have to make. Yeah. So the Pólya tree comes with two parameters. One parameter is that sequence of partitioning subsets, and it really has to be a nested sequence of partitioning subsets. B null and B1 get refined to B null null, B null 1, B1 null, and B1 1, which again get refined to B 0 0 0, B 0 0 1, all the way down to B1 1 1, etc. And we need the sequence of the orange parameters for the conditional splits. At this moment, it's a little bit of a downer, yeah? Because my cartoon on the right-hand side was easy. But if using the Pólya tree, you need to specify these infinite sequences of parameters, that's a bit tedious. Fortunately, it's not all that difficult. There's some obvious default choices. And these obvious default choices, they are maybe easiest to understand by thinking about prior centering, like by making appropriate choices of the orange and the purple parameters. We can center the Pólya tree model at some desired prior mean. So the F star here becomes my desired prior mean. In particular, you have two choices. These are two alternative choices. You don't have to do both at the same time, one or the other. If the partitioning subsets, if those are the dyadic quantiles under the desired base measure, dyadic quantiles, I mean, for B null and B1, we would just use to split at the median. For B null null and B null 1, we use to split at the first quartile, the median, and the third quartile, and so on, right? So if we use dyadic quantile sets under the desired base measure, and if we choose the orange parameters to be symmetric, like those are symmetric beta distributions, then you achieve the prior mean to be exactly the desired F star. Alternatively, we can use arbitrary purple parameters. So you could use arbitrary purple guys and then choose the orange parameters to be essentially the splitting probabilities under the desired base measure. If you want the base measure to be some, for example, a standard normal, then the alpha epsilon 0 has to become the conditional probability of blah blah given blah blah. Yeah. So that solves half of our problem of choosing hyperparameters. Oh, this is kind of sloppy in my notes here. I only said, I said appropriate choice. Oh, so here's one of the reasons why the Pólya tree might be attractive as an alternative to the Dirichlet process prior. You can actually get continuous distributions. Not always, but if you make an appropriate choice of the alphas, you get continuous distributions. I hope I don't get it wrong now out of memory, yeah? But I believe the following thing is true. If you use, for example, the alpha sub, let's denote epsilon 1 for epsilon m. By this I mean an alpha parameter for a split at level m. So when we have already a binary index of length m, if this is like level m of the tree construction, if this is equal to c times m square, I believe that's true. So if this grows fast enough, say with m square, then you get a continuous distribution. For example, we could use the orange parameter cm square. Now you only have to specify the c. Now we are down to a single parameter that we have to specify. Then you get a continuous distribution, and there is applications where it's important that you have a continuous random probability measure. For example, there's a nice old paper by Berger and Guglielmi who actually used it in an application. And here's a funny piece of trivia. Turns out if you choose the orange parameters such that alpha sub epsilon is the sum of the descendants, which by the way would not be, this by the way is not implied, like this one obviously is not, does not comply with that requirement. And that's good so, because I just claimed that with CM square you get a continuous distribution. Whereas under that requirement down here, it turns out you recover the Dirichlet process, and the Dirichlet process generates discrete distributions. So that better not be the same, right? But so here's an alternative definition of the Dirichlet process. The Dirichlet process is just a special case of the Pólya tree. There's a reason why I'm starting to number the definitions, because it will turn out just about anything that we discuss, always the Dirichlet process drops out as a special case. That's a bit typical. The Dirichlet process is a non-parametric base, a little bit what the normal distribution is in parametric inference. Yeah, it often drops out as a special case. So it's widely used, the Pólya tree, not as much as the Dirichlet process mixture, but still there's quite some literature on it. And I had a little example, but in the interest of time, I would actually like to skip the example because I still want to get to the last one. So here was a little example. Let me just point out, I'll just jump to the result of the example. This was about an event time distribution. An event time distribution under two different treatments. So there are two different treatments of, I think it was leukemia. These are, I think it is time to progression. And there's two different distributions for time to progression. And under a parametric model, you might estimate these two distributions. So here is say G1 and here's the estimate for G0. And on the left side, you see similar things under non-parametric prior. And in this particular case, we actually used the Pólya tree prior. And you can see that, for example, there's this second bump here. Yeah? This second bump, this secondary mode, which seems to be for real because, I mean, this comes from the posterior from the data. That's totally, you totally lose it when you just use a parametric model because the parametric model doesn't allow that. But obviously for those patients who fall into the secondary mode, it's actually very important. This is a time to progression, so it's actually a desirable thing. So that's all I wanted to tell you about that example. And I still want to briefly talk through the last construction. So we had the Dirichlet process model, Dirichlet process mixtures. We had the Pólya tree prior. Didn't tell you much about it, just to move on. And here's one more, which is becoming increasingly more popular. One of the reasons why it's becoming increasingly more popular is because computation is not that much more difficult than in a Dirichlet process mixture. At the same time, though, it's much more general. And maybe the easiest thing to do is, before I talk you through the formal definition, I'll show you on my little whiteboard. I'll show you the same construction. So here's the problem. We want to generate, I want to generate a distribution on my desired sample space X. So here's my sample space X. And the aim is, in the end, I want to have a distribution on that X, yeah? I want to already give away the distribution, the random distribution will be discrete. So what you should expect to see here is a bunch of point masses, right? Here's the construction, and it's a very simple construction. That's why it's so popular. In a first, this is my desired sample space, and I already know. So let's already do this one. I already tell you that my random probability measure will be discrete. So I can represent it as a summation of point masses. And sorry to switch notation on you. Earlier that was P sub H for the Dirichlet process. Now let's call it eta sub H. There's no good reason. Yeah, it's just where I copied it from. Eta sub H times a point mass at location mu sub H Apologies, earlier it was P sub h and location was M sub h. For no good reason, I changed notation here. So that's what I want to get eventually. So this on this axis will be the mu sub h, the locations of the point masses. What I'll do is, for the construction, we first will augment the space by adding here the R plus. So here's the positive real line. On the positive real line, let's denote it with eta sub h tilde. Eventually I'll have the f. Before I get the f, let's actually copy that f down here. So eventually I'll get that f, which is a random probability measure. Before I get the f, I will have an f tilde, which uses probability masses eta tilde. So this is just a random measure. Not yet normalized. And this one is a random probability measure that will be normalized. And a very simple, all what we'll simply do is the eta sub h will be the eta tilde divided by the sum of the eta tilde, right? So I'll just simply normalize it by dividing by the sum of the eta tilde, praying that that sum converges. So I've prepared everything. All I have to tell you now is how we get the mu's and the etas. And it's actually a very simple one. What we need is we'll generate a Poisson process. So we'll generate the mu's and the eta tildes from a Poisson process. So that Poisson process, let's make the Poisson process in blue. Poisson process is a point process. So that will throw some points around that space. Do you see how I threw my points? Intentionally, I generated in my little by hand Poisson process generator. I generated many more points close to 0. Here's 0 for the positive real line, like small. And remember the positive real line by the label that I put on the line with the eta tilde already gave away. That the positive real line will eventually correspond to the probability masses. So that means many of my probability masses are small. It's good so, because otherwise I might have no hope of that sum of eta tilde converging. So I generate these from a Poisson process. It's an inhomogeneous Poisson process. Otherwise I would have to generate my atoms all over the space, right? It's an inhomogeneous Poisson process. So I need the Poisson intensity. I'll draw here the Poisson intensity. Let's call the Poisson intensity nu. That's just common notation in that literature. And here's the Poisson intensity. It looks a little bit like a rooftop. I'm really bad at drawing, but can you think of a rooftop? Like it's very high, close to 0 for very small weights, and then it flattens off. Can you see I'm copying the picture on the slide on the left side? The slide on the left side, of course, looks much better, yeah? But in my picture, I can show you now the last step of the construction. So now I have my realization of the Poisson process. So I have here a random configuration under the Poisson process. Each of these is like a pair, mu sub h, eta tilde sub h. What I do now with each of these pairs, you take each of these pairs. Let's do that in gray, so don't mess up my picture too much. I take each of these pairs, for example, this pair here, and rotate it up. Then what we are getting is a pin standing here, right? Same way we are taking this point mass here, rotate it up and get a pin standing here. We are taking this point mass here, rotate it up and get a pin standing here, rotate this guy. And in the end we are getting, so this guy gives me a pin here. So in the end we're getting all these little pins. And voila, that's it. This thing here is my F tilde. That was it, yeah? Did you see how simple it was? So it was really just It was a two-step construction. Generate the random configuration under your Poisson process in blue. The Poisson process generates these pairs, mu h eta tilde h, and now simply use the mu h as the location of the point mass. So this is exactly the mu sub h, and use the eta h tilde. That's the eta h tilde. Use that for the probability mass at that location. That's it. That's the construction. So it's very elegant. That's the F tilde. That F tilde construction, all what you needed for the F tilde construction, we needed that blue Poisson intensity. So we needed that Poisson intensity. I should spell it out. It's mu of the pair mu and eta tilde, right? Give me a blue nu, and I can, and you have a machine to generate a random measure. That random measure, by the way, has a name. It's called a completely random measure. It turns out there's a whole family of those. And then let's call the probability measure that corresponds to it. Let's call that normalized random measure. And that's it. That's it. It's a big family. It's a big family of random probability measures. And after the little cartoon, let's go now to the left slide through the formal definition. And you can see exactly what I promised you here. On top, the definition of the normalized random measure. Here's exactly the F that we had. In that, it's discrete. First of all, it's a discrete thing. In that discrete thing, the probability masses are taken from unnormalized probability masses eta tilde, where the pairs mu eta tilde are simply a random configuration under a Poisson process. That is a Poisson process on the desired sample space augmented by the positive real line with Poisson intensity. This is the blue Poisson intensity from the cartoon on the right side. Depending on what intensity you choose, you get a different random probability measure. This picture here is stolen from a paper by Stefano Favaro and G.E.P. And there's a fast-growing literature on these processes. It's very elegant, the whole construction. I could talk you through it in that little slide that still fits on the right side. That's really all that's to be said about it. And even better, it turns out, if you construct a random probability measure F with this construction, if you used it in statistical inference, like if we have now a density estimation problem, if we say yi given f comes from the unknown f, I equal 1 to n, and then we have the prior on the f. It's a normalized random measure, and I already told you for the normalized random measure we just need the only parameter we need. I have to tell you that Poisson intensity. It turns out it's actually reasonably easy to do posterior inference. Turns out posterior inference, f given y, well, it's not as simple as you might hope now. It's not a conjugate pair, but it is still easy. If we have time on Wednesday, maybe we can go through it. It's not difficult. It's like takes 2 slides or so, yeah. But I'm starting to run out of time. So this is a very elegant construction. Different intensity functions give different priors. And let me just point out, usually you don't use the whole generality of the machine. Usually you restrict to some, first of all, a common restriction is to assume that the Poisson intensity it factors into a factor in eta tilde and a factor in mu. You usually assume it factors like this. And then you assume that the rho comes from some family. For example, this particular construction where we are only left now with the only hyperparameters now, there's a kappa and there's a gamma here. So if I give you the kappa, the gamma, and the h naught, then that triple defines this family, and it's known as the normalized generalized gamma. And surprise, surprise, the Dirichlet process again drops out as a special case for a special choice of the kappa and the gamma. I think kappa equal 1 and gamma equals 0, something like that. Yeah, kappa equal 1, gamma equals 0. The Dirichlet process pops up again as a special case, and will keep on popping up always as a special case. That's all I wanted to tell you about normalized random measures. It's super elegant, it's super beautiful. You can make good arguments why those are more useful than Dirichlet process mixtures, although they're not that much more difficult. Let me just point you maybe like these two are nice papers to review for posterior inference in these models. And I still want to use my last few minutes of glory to talk through random effects distributions, unless this is also a good moment to ask any questions, comments, complaints. I mean, disclosure, we are running over everything here quite fast, yeah? I mean, if you know these things, there's nothing difficult that happened, but if it was the first time you saw Dirichlet process and Pólya tree, then this was really fast. But I'm trying to cover things so that you get the broad idea. And then if something really seems to strike you, like it's something that you need in your own work, then of course you need to go back and read up into for more details. So I would still like to quickly talk about random effects distributions. There isn't that much to be said about it. That's why there's only 2 more slides coming up on it. Really all what I wanted to talk you through is an example. And that example, maybe all what I should show you is this picture here. So I can't resist to tell you what the nature of the data is. The nature of the data is 3 dead bodies. Yeah. So what they do actually, they have like just clinically brain dead bodies, and then you're doing some experiments. And at the bottom line of these experiments, you're looking for peptide tissue pairs. Like the whole purpose is you're looking for peptides that preferentially bind with certain organ tissues, because that could be potential targets for treatment design, etc. But so in the end, you look for different pairs, and they look at many possible ones. So the experimental units are these pairs where the peptide preferentially binds to the particular tissue, and that would result in the red lines. And the picture is the picture of the data. If you hit a lucky pair where the peptide preferentially binds to a particular organ, then you should see a red line where the count increases over these 3 dead bodies. Yeah. So our problem is, among all these many spaghetti, there's many black spaghettis, blue spaghettis, and red spaghettis. Out of all these many spaghettis, we want to find the red spaghetti. The spaghettis are parametric. You can easily imagine they are parameterized by what we use here in the end is we just use 2 parameters, the beta and the delta. Those are of interest. Depending on the beta and the delta, if both the beta and the delta, if delta greater beta greater 1, that corresponds to the red spaghetti over there. It's not immediately obvious, but it's not difficult either. Yeah. So the red spaghetti are those where delta greater beta greater 1, and each pair has its own delta beta pair. It's like it's a random effect. It's a random effect specific to the peptide tissue pair, and so we want to build now a statistical inference model. There's a sampling model. I didn't talk you through that at all. The sampling model just uses Poisson distributions, and then we need a random effects distribution for the beta delta pairs, and we have to make an assumption about the random effects distribution. That's where the rubber hits the road. Yeah, however you say that nicely in French, I don't know. The random effects distribution, if we were to use now a standard thing, just a bivariate normal, we would totally miss the issue, because what we want to do is, see down here is the, this is the beta and this is the delta. And remind you again, we are after delta greater beta greater 1. So we are actually after these guys. These guys are the red spaghetti of interest. So fitting and all the dots, they're simply the beta I, delta I pairs. Fitting a bivariate normal to these red dots, we would totally miss it. Like we want to identify the guys in here because they are hopeful treatment targets for binding peptides to certain organs preferentially. Like if you want to deliver a treatment specifically to kidney tissue, then you might want to make use of blah, blah, yeah? Well, what do you think we did? Our probability model for the random effects distribution, we used the Dirichlet process mixture of normals because sloppily speaking, BMP models, a non-parametric Bayes is always right. See, if I assume a bivariate mix, if I assume a bivariate normal, I will probably miss that particular distribution. Like when you use a bivariate normal, you're bound to miss what's going on here. Whereas if you use a non-parametric Bayes model, non-parametric Bayes is always right in the formal sense of full support. Like the prior probability model for the random distribution has full support. Any true distribution or prior puts non-zero probability mass in any appropriate neighborhood of any true distribution, so we can recover it potentially. That's what this story is about. And that brings me to the end of what I wanted to talk you through today. Any final questions, comments? If you send me or Alex email, maybe too fast, was it too, should I ask for more? I could have stopped more often for questions, feedbacks. How do you feel about it? I mean, happy to do that, yeah? Sometimes it's better to do less in more detail. So any comments, feedback, welcome. Email me or email Alex, and we'll accordingly proceed adaptively with Bayesian adaptive design tomorrow and on Wednesday. Yeah.
Yeah. Thank you, Peter.
Thank you. So otherwise, the plan is on tomorrow we do regression and on Wednesday we do clustering. Yeah.
Mm-hmm. I really enjoyed the lecture. Thank you so much. I just would like to remind everyone that we are recording these lectures, and Guillermo will probably organize them, edit them, and make them available in the CRM website. We can send an email to everyone after the short course is over. But I guess we see everyone tomorrow, right?
Okay, well, thank you. Au revoir.
Au revoir. Merci beaucoup. Hein? Merci beaucoup. Bye-bye.
Ciao.
Thank you.
Bye.
See you tomorrow. Bye.
Bye.